Good morning and welcome to our discussion about mixtures. We said that if something is pure, that means there is only one element or one compound in the sample that we're observing. Here we've got some examples of pure things and mixtures. A mixture simply means you've got more than one element or compound in there. So basically, this first one, it says here pure solid. I wouldn't go so far to say this is a solid, but I can see this is made of one element. So this is pure. It's not a mixture. This is a pure substance. Get used to these. These are called particle diagrams. They love them in AP Chem. This second thing, it says here it's a mixture, and it's obviously a mixture because it's made of this, which is one element. So one little smooth hard ball is one atom, and this is a molecule made of two atoms. So yeah, this could be a gas. This could be something from group 8, such as helium, and this could be, I don't know, N2 or Cl2, whatever. You know, most gases are diatomic. This is a pure gas, right? There's just one compound, so that's a pure substance, not a mixture. This one is cheeky because it looks like it's two things, but this is an ionic lattice. Remember, ionic lattice is made of usually, well, not usually, always two ions, and they're just spread out like this evenly. If you see this, you should know this is pure, even though it looks like it's two things. This is obviously pure. It's just compound made of two different atoms, but it's always the same compound. So this is pure, not a mixture. This is obviously a mixture. Again, I don't agree with this like gas mixture. And I also don't agree with this element plus compound. This to me looks like one compound made of two same elements, such as O2, and this looks like a compound made of two different elements. So this, I would say, this is a mixture. I wouldn't go so as far to say it's a gas. Now, when we have mixtures, we still use a lot of moles and grams and conversions and percentages, but this question is just slightly different. So let's do a couple and see what that gets us. Check this out. So it says a 4-gram mixture of KCl and NaCl contains zero point 0.7 grams of K. Only K. What is the percentage of KCl in the mixture? How to determine this? First of all, I will use zero point 0.7 to calculate how many moles I've got, how many moles of K I've got, right? So 1 to 39, which is the molar mass of K, is x to zero point 0.7, same like we did so far, and I have this many moles of K. Now, I know KCl is made of one atom of K and one atom of Cl. So if I got this many moles of K, I also must have this many moles of KCl, right? And if I know that I got this many moles of KCl, I can calculate the mass of that, right? Because that's what I need. I need the percentage of KCl. So I would just go first calculate the molar mass of KCl, which is this much. And then I'll say 1 mole of KCl is that much. And 0.018, I don't know what this is here, to X. And I've got this many grams of KCl in the mixture. But the total mass of the mixture is 4 grams, right? So I just divide 1.34 with 4, and then I'll get a fraction. So I have to multiply by 100. And poof, I get a percentage of KCl in the mixture. You can see, I mean, pretty simple. But these questions often require a bit more time. Check this out. This is, again, a particle diagram, something they love to use. And you should know that this means 3 atoms, but it also can mean 3 moles. So basically, look at this. What did they say? C shaded circles are C's, and small filled dots are H's, and these uh, bigger white dots are just oxygen. So they want to say which one of these contains the greatest percentage of carbon by mass. Now, if you take a look at this, let me just give you the answer so it's easier to overview this, to review this. So basically, here what we've got is 3 carbons, and molar mass of carbon is 12, right? Oxygen is 16, and hydrogen is 1. So basically, if I want to calculate the percentage mass of carbon in here, I can just go, I got 3 carbons, right? 3 moles of carbon, right? So 3 times 12 divided by the whole mass of all this, which is 12 times 3 plus I've got 9 oxygens here, and each one is 1 mole per liter. So I'll get that this is 80% carbon, right? This one is, see, there is a trick here. Each of these has 3 hydrogens next to it, but this one's got 2. That's a trick. So basically, you've got 12 times 4 carbons, but then you only got 11 hydrogens, and then you get that this is actually a slightly higher percentage of carbon by mass than A. These two we don't even want to calculate. Again, you want to do this as quickly as possible. You don't want to calculate this. Why? Because here still carbon to hydrogen is 1 to 4, which is really bad. It's worse than here, right? There's less carbon percentage wise. Plus, you've got oxygen, which is 16 grams. So this is like less than 50%, like way less than 50% carbon. This one is similar, but it is for sure worse than this. Because see, this one is missing some hydrogens, but it's got 2 oxygens, which is way more than this. Way more oxygen, way less carbon. So again, you want to do this fast like this. You don't want to calculate every single thing. Now take a look at this. Student is given 5-gram samples, each a mixture of these two. So you've got 2 samples, each is 5 grams, and you know they're a mixture of this one and this one, but you don't know how much, right? Which piece of information could be used to determine which mixture has a higher proportion of MgCl2? So what do you need? What piece of information? Like here, you need to determine the percentage of MgCl2 in this. The mass of Cl in each mixture. I mean, yeah, the mass of Cl would help, although you wouldn't be able to calculate only through that, but it will be a useful piece of information. The volume of each mixture, I mean, you can see that we didn't even talk about volume here. It has nothing to do with it. Number of isotopes of Ca and Mg has nothing to do with this. Reaction of each mixture with water. Again, you can see this has nothing to do with reactions with water. So for sure, this is A. This is the only piece of information which is useful, even though that piece of information alone will not help you solve the problem. Yeah, so it's A. Let's see this one. A sample of a solid labeled Ki may be impure. Impure just means it's a mixture. There's something else in there. It's just pure. It's not pure Ki, or maybe not pure Ki. So student analyzes this, and he finds that this sample that you've got is 40% iodine. Pure Ki is 76% iodine. So again, there is something else in there. What is it? A, the sample contains only Ky. No, because then this would be correct, and we got way less. The sample contains Ki and NaI. Now let's see. K has a bigger molar mass than Na. So actually, if you add an NaI, percentage-wise, the mixture will have more iodine than 76, not less. Why? Because as you're adding NaI, you're adding percentage-wise more iodine because Na has smaller mass than potassium, which you're comparing to. Okay, the sample contains Ki and Lii. Again, Li has a smaller mass than K. So if you're adding Lii, you're basically increasing the percentage of iodine in the mixture. And then the sample contains Ki and KCl. I mean, pretty obvious. If you add KCl, basically there's gonna be less iodine, right? Because I mean you're adding other stuff and not iodine, right? So it can drop from 76 to 40. So the only possible explanation is D. Yep. Now, I gave you this one on purpose. See, College Board has a rule that a lot of these questions have to involve something done in the lab. So I'm going to give you these questions sometimes so that I can teach you gradually about uh, what can be done in the lab in this regard, because they don't have a lab plan, but they still give these questions. And also, even if you went through high school chem, you won't be going through all of this. So actually, you have to teach you step by step. So see, the percentage of sulfate in a soluble salt is determined grammetrically by precipitating the sulfate as BaSO4. First of all, gravimetry is just analyzing something by measuring mass. That's all it is. So how is it determined? Precipitating the sulfate as BaSO4. Precipitation just means that I have something in the water here, and then I add another chemical that is going to make something from my solution form a solid on the ground, and that solid is called a precipitate. And then, as you can see here, I'm working with that precipitate. So failure to do which one of these could cause error in the analysis. So I've got the precipitate BaSO4 on the bottom here that I want to measure. I want to analyze it because this is gravimetry. I need to measure the mass of that, right? So what could cause an error? One, failure of what? So failure to account for the mass of the weighing paper when determining the mass of the sample. So I mean, in the lab, you're going to measure everything on an analytical balance on weighing paper. Sometimes you might use other things, but usually it's going to be on a weighing paper. So how do you do this? You first put the weighing paper, and you measure the mass of the weighing paper. Then I add the precipitate, and then I measure the weighing paper with the precipitate, and then I minus the second measurement from the first, right? Analytical balance can do this by itself, but definitely failure to account for the mass of the weighing paper will cause the error in weighing my BaSO4. So yes, one is correct. Two, measure the pH of the solution during the precipitation reaction. Okay, this is a longer story, but pH influences the precipitate formation. So if the pH is wrong, you won't get enough precipitate. So again, we will explain this more and later in unit 7, is it? Acid and bases. Failure to wash the precipitate. Yeah, so when you're doing gravimetry, so I'm taking this precipitate, the first thing I want to do is wash it. Why do I wash it? Because there are other things in the water, other ions, which might stick to the surface of the precipitate. So if I just pour this out and I measure it, first of all, it's going to be wet, so it's going to add mass. So I want to first wash it with water to remove the ions, and then I will heat it to remove the water, because I don't want to measure with the water, right? So yeah, fail to wash the precipitate will definitely cause an error. Heat the BaSO4 precipitate to constant mass. Again, this is a common practice in the lab. When you're doing gravimetry, you want to measure that precipitate and you want to remove the water, right? So to remove the water, you heat it. But you heat it once for, let's say, 20 minutes, 10 minutes. Then you measure the mass. Then you heat it again. And then you measure the mass. If the second mass is different than the first mass, that means there's more water in it. So you need to heat it again 3, 4, 5 times until you get the same mass at least twice. That is what this means. Heat the precipitate to constant mass. You keep heating it to remove the water. So actually, all of these are correct. This is I just noticed it's not A, B, C, D. So all of these are actually correct. Okay, try to do the questions. Don't get confused, because in the quizzes from this chapter, there might be questions which are going to include things that can't know without knowing the next chapter, 3 chapters. So pay attention to that. Let me know if you need anything, and bye bye.